Practical number 3. Prove that 4 does not divide a square plus 2 for any integer a. Now we can prove this by using contradiction. Suppose, say, using contradiction, suppose 4 divides a square plus 2. This implies a square plus 2 is multiple of 4, so say it is equal to 4k for some integer k. This implies, if you simplify this will get a square is equal to 4k minus 2. Now we can simplify it further. A square is equal to 2 times twice k minus 1. So this implies this 2 divides a square, but this implies 2 divides a into a. Now since 2 is a prime, by Euclid lemma 2 divides a. Okay, and this implies 2 divides any integer a, but which is contradiction that 2 divides only even integer, not odd integers, and that is since 2 does not divide 3, 2 does not divide 5, and so on. So we get this contradiction because we assume here 4 divides a square plus 2, and therefore 4 does not divide a square plus 2. Example number 2. Prove that there are no integers x and y such that GCD of xy equal to 3 and x plus y equal to 100. Again, suppose again by using contradiction, suppose there are xy, there exist x and y such that GCD of xy equal to 3 and x plus y equal to 100. But since GCD of x and y equal to 3 implies 3 divides x and 3 divides y, but this implies x is equal to 3 times k1 and y is equal to 3 times k2 for some integer k1 k2 belongs to z. Now put these values in the equation x plus y equal to 100. So we get thrice k1 plus thrice k2 is equal to 100. So this implies 100 is equal to 3 times k1 plus k2, but this implies 3 divides 100, and which is contradiction that which is not possible, okay, which is not possible, which is contradiction, and hence contradiction that 3 does not divides 100, and hence the proof. From this we can say that there does not exist, or there are no integers x and y such that GCD of xy equal to 3 and x plus y equal to 100. Now next example number 3. Find all primes that divide 50 factorial. Now we know that the 50 factorial can be written as, this 50 factorial can be written as 1 into 2 into 3 into 4 into 49 into 50. Okay, so the prime number 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47 are factors of 50 factorial, and so these are the only prime, and these are the only primes that divide 50 factorial. Suppose if we take a prime which is greater than 50, suppose we take a prime which is greater than, or say greater than 50, say 53, but 53 is not a factor of any number between 1 to 50, and hence this implies, these are the only prime numbers. You can write this statement here. These are the only prime numbers which divides 50 factorial. You can write this statement here. Okay. Now next example number 4. Example number 4. Prove that 10 factorial congruence to minus 1 mod 11. 10 factorial congruence to minus 1 mod 11. So we know that the 10 factorial is equal to 10 into 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1. Now this from this we can say that if we take 4 into 3, say since 4 into 3, which is equal to 12, which is congruent to 1 mod 11. Then next, if we take say 6 into 8, 6 into 8, which is equal to 56, which is congruent to 1 mod 11. So next, if you take say next is say 5 into 9. If you take say 5 into 9, which is equal to 45, which is congruent to 1 mod 11. So 9 is gone, 5 is 8, 6, 4, 3, and now if we take next is there is one correction, actually here not 6, here is 8, where here is a 7, sorry, 7 times 8 is 56. So 7 is gone, 6 is there. So 6 into 2, which is equal to 12, is congruent to 1 mod 11. So if you check, there is 1 and 1 congruent to 1 is congruent to 1 mod 11. So there is 1 is there, 2, 3, 4, 5, 6, 7, 8 and 9. So what this implies, 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9, all these congruent to 1 mod 11. 1 mod 11. Now since 10 is congruent to minus 1 mod 11, since 10 minus minus 1 is 11 and 11 divided 11, so 1 into 2 into 3 into ... 10 congruent to 1 into minus 1 mod 11. But this implies 10 factorial is congruent to minus 1 mod 11. Hence the proof. Now the next question. 89, say next question 89, say number 89 divides 2 raised to 44 minus 1. So now again, by using the Fermat theorem, we know that if P is a prime, by using Fermat theorem, if P is a prime and P does not divides A, then A raised to P minus 1 congruent to 1 modulo P. So here P is 89 and A is equal to 2, and 89 does not divide 2. 89 does not divide 2. So by using Fermat theorem, 2 raised to 89 minus 1 congruent to 1 modulo 89. So this implies 2 raised to 88 congruent to 1 modulo 89. So this implies this 88 can be written as 2 raised to 44 raised to 2 congruent to 1 modulo 89. So any number that is a square congruent to 1 modulo 89. So if here a is equal to 2 raised to 44. So this implies a square is equal to a is congruent to, this implies a is congruent to 1 modulo 89 or a is congruent to minus 1 modulo 89. That is, this implies since a is equal to 2 raised to 44, this implies 2 raised to 44 congruent to 1 modulo 89 or 2 raised to 44 congruent to minus 1 modulo 89. So this implies 89 divides 2 raised to 44 minus 1 since it is congruent to, or 89 divides 2 raised to 44 plus 1. So and see, this is not or, actually you can say this is and, because now the next example, next example, 7 divides 2 raised to 5 plus 5 raised to, that is 2222 raised to 5555 plus 5555 raised to 2000. Now if you let us break this problem into two steps. First, if you divide this 2 by 7, we get say 21. Then if you take subtraction here, this will be equal to 2. Then again 49. So remainder is 3. So this 2 congruent to 2222 congruent to 3 modulo 7. So this implies 2222 raised to 5555 congruent to 3 raised to 5555 modulo 7. Now since by Fermat theorem, since 7 does not divide 3, this implies 3 raised to 6 congruent to 1 modulo 7. Now we want to reach up to 555. Say suppose again if we divide this 5555 by 6, we get if we divide this by then first we get here 954, 1 again say 2, then again if we take here 3, then this will be equal to 5. So remainder is 5. So we have to take the power 3 raised to 6, 3 raised to 6 raised to 925 congruent to 1 raised to 925 modulo 7. So this implies if you multiply this 925 by 6, we get 3 raised to 5550 congruent to 1 modulo 7. Say this is equation number 1. We want to reach up to the power 3 raised to 555. So again we know that what is 3 square. 3 square is equal to 9, which is congruent to 2 modulo 7. So 3 raised to 2 congruent to 2 raised to 2 modulo 7. So this implies 3 raised to 4 congruent to 4 modulo 7. And if we multiply again, if we take one power here, 3 raised to 4 into 3 congruent to 4 into 3 modulo 7. This implies 3 raised to 5 congruent to 12 modulo 7. So this implies 3 raised to 5 congruent to 5 modulo 7. Say if you multiply these two equations, say equation number 1 and equation number 2, say this is 2. If you multiply 1 and 2, if you multiply 1 into 2, we get 3 raised to 5550 into 3 raised to 5 congruent to 1 into 5 modulo 7. So this implies 3 raised to 5555 congruent to 5 modulo 7. Say this is equation number 3. Similarly you can find 555 raised to 2. Okay, so now if you divide next 5555 by 7, we get 1555 divided by 7, then we get this is equal to 49. Remaining is 6. This is equal to 63. Remaining is 2, and next it is 21. So remaining is 4, and hence 5555 congruent to 4 modulo 7. Now this implies 5555 raised to 2 raised to what? Raised to 2 say 2 congruent to 4 raised to 2 modulo 7. Now so we want to determine the power of 4 raised to 2222. Now again by Fermat theorem, 7 does not divide 4, so 4 raised to 6 congruent to 1 modulo 7. Now again if you divide 2 by 2000, say here if you divide say 2222 by 6, then if we divide by 6, then first it is equal to 3, then next 42, then remaining 2, next 0, and remaining is 2. So we have to take the power 4 raised to 6 raised to 370, which congruent to 1 modulo 7. So but 4 raised to 6 raised to 376 into 370 is equal to 2220. 2220 congruent to 1 modulo 7. Say this is equation number, say 4. Now we still want to determine 2 power of 4. 4 raised to 2. So 4 raised to 2 is congruent, is equal to 16, which is congruent to 2 modulo 7. 2 modulo 7. So is the question. 4 raised to 6. So if you multiply these two equations, say this equation number 5, if you multiply these two equations, we get 4222 raised to 0 into 4 raised to 2 congruent to 1 into 2 modulo 7. But this implies 4 raised to 2222 congruent to 2 modulo 7. Okay, so say this is equation number 6. So this is equation number 6. So from 3 and 6, from 3 and 6, 3 and 6, we can say that 2222 raised to 5555 plus 5555 raised to 2222, which is equal to what is 222 raised to 5 from 3? It is 3 raised to 5555 plus this is equal to 4 raised to 2222. This will be equal to, now this is congruent to 5, and this is congruent to 2 modulo 7. This is also modulo 7, but this implies 7 modulo 7. But 7 modulo 7 means what? 0 modulo 7, and this implies 7 divides this 222 raised to 5555 plus 5555 raised to 2222. Hence the theorem. Hence the proof.